Hey everyone, and welcome to This Explainer. Okay, today we are zeroing in on a mission to demystify what is honestly one of the most intimidating areas of calculus for a lot of people: infinite series with non-negative terms. Listen, if you've ever stared down a sigma notation and felt a sudden sense of panic, you are absolutely in the right place. We're going to build a rock-solid toolkit featuring 3 incredibly powerful tests to help you handle these mathematical puzzles with total confidence. But before we get into the weeds, we've got to talk about the real central mystery here. You see, one of the biggest, most frustrating challenges in calculus is that most infinite series simply cannot be summed exactly. The math is just way too messy. So instead of banging our heads against a wall trying to find that exact perfect sum, we pivot. We ask a totally different question. Does the series approach a finite value, or does it just grow without bound? Basically, does it converge, or does it diverge? That one simple shift in perspective is the key to literally everything we're about to cover. So, to answer that question, here is our roadmap for today. Number 1, the integral test. Number 2, the direct comparison test. Number 3, the limit comparison test. And finally, number 4, choosing the right test. All right, let's dive right into tool number 1, the integral test. This is where we study an improper integral instead of the series itself. So the integral test is based on this genuinely brilliant idea. Instead of wrestling with a clunky, difficult series directly, we completely sidestep it. We study a related improper integral that uses the exact same function. But hold on, before you even think about integrating, you have to run through a mandatory safety checklist. Your function absolutely must be 3 things: continuous, positive, and eventually decreasing, which just means it might bounce around a bit at first, but it eventually has to head downwards. If even one of those conditions fails, you've got to abort the test. But if they all check out, then the series and the integral share the exact same fate. They're tied together. They will either both converge or both diverge. Now, I need to wave a massive red flag right here. A super common mistake, and I mean people do this all the time, is believing that whatever numerical value you get from evaluating the improper integral is the actual sum of the series. That is unequivocally 100% false. The integral test only checks for convergence or divergence. Think of it like a compass telling you which direction to go, not a GPS giving you your exact destination. It does not compute the sum. Keep that straight, and you're going to avoid one of the biggest pitfalls in all of calculus. And here's why the integral test is so crucial. It gives us one of the most foundational results in all of mathematics. We call it the p-series result. You are absolutely going to want to burn this definition into your memory because it'll be your main benchmark from here on out. It goes like this. For a series in the format of 1 over n to the power of p, it converges if p is strictly greater than 1, and it diverges if p is less than or equal to 1. Like I said, you're going to use this fact over and over and over again with our next 2 tools. Which brings us to tool number 2. The direct comparison test, comparing directly with known behaviors. Okay, so you're going to want to pull this tool out when evaluating an improper integral is either completely unnecessary or just way too complex to even bother with. Instead of integrating, we just compare our mystery series directly to another series whose behavior we already know, like, say, that p-series we literally just talked about. There are 2 successful scenarios here. First, if your series is strictly smaller than a known convergent series, it's trapped, right? So it must also converge. On the flip side, if your series is strictly larger than a known divergent series, it's being pushed straight to infinity, so it also diverges. It's actually wonderfully intuitive when you picture it. But you guessed it, here comes another major warning. Do not reverse these inequalities. Students do this all the time. If you do the math and find out your series is larger than a convergent series or smaller than a divergent series, well, congratulations, you've learned absolutely nothing. The test is completely inconclusive in those cases. You absolutely must bound it below a convergent series or above a divergent one. Let's actually look at how this plays out in the wild with a quick example. Take the series 5 divided by the quantity 2n squared plus 4n plus 3. I mean, integrating that looks like a total nightmare, right? But just look at the denominator. 2n squared plus 4n plus 3 is clearly larger than just 2n squared by itself. And because the denominator is larger, the overall fraction is actually smaller. So our messy, complicated series is strictly less than 5 over 2n squared. And what is that? That comparison series is just a constant multiple of a convergent p-series. Because it's smaller than a convergent series, our original series must converge too. Boom. Done. All right, up next is tool number 3, the limit comparison test, comparing ratios instead of inequalities. So what do you do when finding those nice clean inequalities becomes a frustrating mathematical maze? That is when you bring in the heavy artillery, the limit comparison test. Instead of fighting to find direct inequalities, we compare the ratios of the terms using a limit as n approaches infinity. There are three possible outcomes here, but the most common one by far is when your limit equals some positive finite number c. If you get a positive finite number, both series behave exactly the same. They either both converge or both diverge. There are also a couple of highly specific caveat rules if the limit is exactly 0 or exactly infinity, but those only work if the comparison series behaves in a very specific way. Now, I really need to highlight the blind spots here because the math can totally break down on you if you aren't careful. If your limit is 0 but your comparison series diverges, you have no conclusion. Nothing. 0. Likewise, if your limit is infinity but your comparison series converges, again, you have no conclusion. A lot of people incorrectly jump to conclusions in these exact scenarios. Please don't be one of them. So how on earth do you pick a good comparison series for this? Well, here is an absolute pro tip for you. Ignore the noise. You just want to keep the dominant terms. Look at this nightmare expression. 2n squared plus 3n in the numerator all over the square root of 5 plus n to the fifth. If we strip away the lower order noise, meaning we just drop the 3n and the 5 entirely, it behaves essentially just like 2n squared over the square root of n to the fifth. Using just some basic algebra that easily simplifies down to 2 over the square root of n. And just like that, we immediately know we should compare it to a divergent p-series, making our limit math an absolute breeze. Which brings us to our final section, the field guide. Let's talk about choosing the right test. All right, we've got our three tools, so let's put together a foolproof battle plan for when you're actually out there facing an unfamiliar series. First up, ask yourself question 1. Can I write the terms as values of a continuous, positive, decreasing function? And, crucially, is it something I can actually integrate easily? If the answer is yes, grab the integral test. It's direct, it's elegant, and it will get the job done. Now, if integration looks like a complete nightmare, you move to question 2. Can I immediately compare my terms using simple, obvious inequalities? Like, are you just adding or subtracting a constant to a familiar p-series or a geometric series? If those bounds jump right out at you, then pivot and use the direct comparison test. But what if you're staring at some giant, ugly fraction full of competing polynomials and roots? That leads you to question 3. Are the terms complicated, but their dominant parts are actually pretty easy to identify? If you can easily chop away the lower order noise to reveal a nice, clean comparison series, then the limit comparison test is going to be your absolute savior. So let's do a quick rapid-fire recap to lock this all in. The integral test swaps your series for an improper integral. The direct comparison test relies on establishing strict, solid inequalities. The limit comparison test cuts through the algebraic mess by analyzing ratios. And listen to me on this one. Above all else, always check your hypotheses and prerequisites before applying any theorem. Skipping those prerequisite checks is a fatal error that will inevitably lead you down the wrong path. But all of this brings us to one seriously fascinating final thought. We now have these three incredibly powerful tools in our arsenal, right? But they all share the exact same limitation. They only tell us whether a series converges or diverges. They do not compute the exact sum. So, if we know for a fact that a series converges to a finite value, how in the world do we actually go about finding what that specific numerical value is? Well, that is a fantastic question, and exploring the techniques to finally unlock those elusive sums will be the next thrilling step in your mathematical journey. Thanks so much for joining me on this explainer, and as always, keep learning.